Hello, everyone. My name is Maolin, and the title of the paper I'm going to talk about is called Improved Divergence-Free SPH via Priority of Divergence-Free Solver and SOR. This is the outline of our report. First, introduce the pressure solver in the existing SPH method, then our specific improvement method, and finally the result and the summary of the experiment. In SPH, the pressure solver is one of the most important modules, which solves the pressure inside the fluid particles. It makes the motion process of particles conform to the NS equation. Algorithm 1 is a simple simulation loop for SPH simulation. Marked in yellow are the pressure solver steps. Pressure solvers of SPH can be roughly divided into three categories, namely equation of state-based pressure solver, density-based iterative pressure solver, and divergence-based iterative pressure solver. The following is a brief introduction to these three types of solvers. First is equation of state-based pressure solver. This method uses the EOS equation to solve the pressure. EOS is expressed as follows, where the left term is the pressure of the fluid particles, and Pi on the right term is the current density of the particles. P0 is the static density of the fluid, and K is the stiffness constant set by the user. By solving EOS, we can directly get the pressure of fluid particles. The advantages of EOS equation is it is easy to implement. The particle pressure can be calculated directly by bringing in the current particle density. The disadvantages of the EOS equation is there are strict restrictions on the time step. Large time step will cause instability, and it needs users to adjust the value of parameter key. Next is density-based iterative pressure solver. This method solves the pressure Poisson equation, PPE, to get the pressure, such as PCI SPH and II SPH. There are two forms of PPE. One is based on density and the other is based on divergence. This type of method used density-based PPE, which can be expressed as this, where ρ0 represents the fluid static density. Rho star denotes the predicted density after accumulating non-pressure force. Delta T represents the time step, and rho T, PT is the current pressure. The advantages of density-based iterative pressure solver is compared to EOS, a larger time step can be used, and the incompressibility of fluid is better than EOS. Disadvantage is there is divergence in the solution process, which affects the stability and performance of the simulation. The two figures is PCI SPH and II SPH. The last is divergence-based iterative pressure solver. Bender and Korscher proposed DFSPH. This method adds a divergence-based PPE on the basis of the second type method to ensure that the divergence of the fluid is zero, and enhance the stability of the simulation. The divergence-based PPE can be expressed as this. Rho T is the current particle density without accumulating non-pressure force, and the divergence V star represents the divergence of velocity after accumulating non-pressure force. The advantages of this method is most of the divergence is eliminated, and the stability of the simulation is significantly improved. Larger time steps can be used, and time efficiency is significantly improved. Disadvantage is the particles still have divergence after the non-pressure force is accumulated by the solver. This affects the number of iterations of density solver. The iterative method of the solver uses Jacobian iteration, and there is room for improvement in efficiency. Considering the disadvantages of DF-SPH, we proposed a new solver order, which reduced the number of iterations of the two pressure solvers. Combining SOR into two pressure solvers further reduces the number of iterations and tests the effect of different SOR parameter omega on the solver in different scenarios. Next, we introduce our method. Let's start with PPE. The original form of PPE based on density is this, where VO represents the original velocity of the particles without accumulating non-pressure force, and delta VNP denotes the change in particle velocity caused by non-pressure force. The detailed derivation process can be seen in the paper. From the above formula, we can find that there are two main types of divergence. One type is the divergence caused by the movement of particles after the last iteration loop, and the other type is the divergence caused by accumulating non-pressure force. The specific code of our algorithm is shown in the figure. Marked in yellow is the accumulation process of non-pressure force and two pressure solvers. The previous method eliminated the divergence caused by particle movement by adding a divergence-free solver, which is divergence VO, but did not eliminate divergence delta VNP. We found that placing the divergence-free solver after the accumulation of non-pressure force can effectively eliminate divergence delta VNP. Since our method eliminates most of the divergence, including divergence delta VNP caused by non-pressure force, the density solver can use a very small number of iterations to solve the particle pressure. Although the number of iterations of the divergence-free solver will increase slightly, the total number of iterations compared to the original method is significantly reduced. Next, we use SOR in the density solver and divergence-free solver to iterate. Compared with the original Jacobian iteration, there is a significant reduction in the number of iterations. Algorithm 2 is a divergence-free pressure solver in DF-SPH. The pressure solution is mainly divided into 3 steps, since the results of the first 2 steps will be carried into the 3rd step for calculation. We only need to modify the formula of the 3rd step to the SOR form. The modified formula of the 3rd step is as follows. Omega is a user set SOR factor greater than 1. When omega is small, the performance improvement is less obvious, while a large omega may cause simulation instability. Through experiments in different scenarios, the results are the best when the value of omega is 1.35. The specific steps are as follows. First, we calculate d rho I divide dt based on the velocity divergence. Next, we calculate the pressure of particle I and the surrounding particle J according to this equation. Finally, we update the particle velocity by this equation. Next, we introduce our results. The following 4 figures show the simulation results of our method in 2 different scenarios. We used this to build the overall program framework and use Maya for rendering. The following 2 tables show the performance of our method compared to other methods. It can be seen that our method requires only a few iterations in the density solver, and both the solver time and the overall time decreased. Compared with other methods, the time improvement factor reaches 1.37. As mentioned earlier, SOR will affect the performance and stability of the simulation under different parameters omega. The picture shows the number of iterations required for constant density solver and divergence-free solver under different omega. The blue one is the divergence-free solver. The red one is the constant density solver. Considering the performance and stability, the result is satisfactory when omega is 1.35. The testing is Denbrick model Dragons. This is a demonstration of the stability of our method under different omega for a scene of a cylinder fluid hitting the wall at a high speed. Omega is 1.2, 1.35, and 1.6, respectively. It can be seen that when the omega is 1.6, the simulation produced instability. There is a track at the end of the cylinder fluid. This picture shows a comparison of simulation stability between our method and other methods in extreme cases. The simulation of cube fluid falling into the ground at a high speed, from left to right and top to bottom, are the results of our method, DF-SPH, II-SPH, and PCI-SPH, respectively. It can be seen that both our method and DF-SPH can be simulated stably. Both II-SPH and PCI-SPH are unstable. Note that we use the adaptive time stepping according to the CFL condition. Conclusion: we proposed an improved fluid pressure solver, which effectively reduces the time required in the solution process by advancing the divergence solver and pre-accumulating the velocity effects of non-pressure force. In addition, we introduced the SOR method to improve the Jacobian iteration used in the previous pressure solver. Without affecting the stability of the fluid simulation, our method greatly reduces the number of iterations of the constant density solver to fewer than 2, which is close to the upper limit of the number of iterations required, while the number of iterations of the divergence-free solver has only a small increase. Thank you for your attention.
Thank you very much for the nice presentation. I see that we already have questions, so Feng Tian, take it away.
Yeah, sure. Okay, thank you for the presentation. I just got the picture. Sorry, I just got questions. Regarding the omega and the parameter you said, looks like different, omega would give you different effect. So at this moment, and you set the omega manually, right? Don't you? And is that possible to set it according to, environment? For example, maybe the liquid, heat different, material, and, to achieve different effect. Is that possible in using your algorithm?
In our experiment, we test the omega in different scenarios, and we find that when it is 1.35, the iteration it need is decreased, and the stability didn't have any decreases. But when omega is larger, for example, 1.6, the fluid seem to be unstable. So we don't think this is relative to the environment, because we test it in many scenarios.
when you talk about the mainnet scenarios, sorry to catch you. And when you talk about mainnet scenarios, can you give me 1 or 2 examples? What kind of scenarios were you talking about?
We test, for example, dam brick mode, and we can show you the video.
Do we have time, Eric?
Yeah, we're good. We're good on time.
Okay. Yeah, go ahead, please. Yeah, maybe very short one.
Like this is the four scenarios we test in this.
Oh.
Yes.
So maybe if I may, I would like to follow up on that question. I'm wondering, so you have different scenarios, but do you have different amounts of water? Because it's kind of different to like flood a whole city or do a splash in a pool or like pour a glass of water. So in your examples, what's the amount of like cubic meters of water, or what just to give us an idea?
Pardon, I don't understand the
okay
question.
So it's my question is about what's the amount of water that is simulated. Is it in the order of like an ocean or a pool or a glass of water?
It's normal water. The particle we use we test is 100,000 1 million. 12
120,000. Yeah,
120,000. Yes, 120,000 particles.
Okay. Yeah.
Okay. Are there other questions? I would, if there aren't other questions, I would like to know, like in the images and videos, like there's some coloring of the particles. Could you comment a little bit on what it represents?
Okay. The color of the particle represents the fluid particle's velocity. White represents a high velocity, and blue represents low velocity.
Okay, I don't see any other question. We do have a little bit of time, so I'll harass you with one more question. So apart from computation time, did you have another mean of comparison with DF-SPH?
We compared with DF-SPH on stability, but this is a demonstration that we have a same stability of SPH. Our main contribution is the time efficient performance, and the stability is not decreased, but it has not too much improvement in this. Yeah.
Okay, we don't have any other questions as far as I can see.